In this video, we're going to look at derivatives of inverse functions, and then of course we're going to move into the derivatives of inverse trigonometric functions. So let's start out with a graph of a function. So here's the graph of a function. This is f of x, and it probably is a quadratic, but this will work for every function, provided of course it does have an inverse. And here is the graph of the inverse function. Now notice how they labeled this point. This is f inverse of a. And the reason they label it as f inverse of a on the original function is because we know that f inverse of a, because domains become ranges and ranges become domains when we find inverses, this is the element of the domain of the original function. And then the way that this is noted is that a then would be the element of the range of the original function. And so this is an element from the domain, and this is the element from the range of the original function. In this notation here, we know that this a now represents, this a down here represents an element of the domain of the inverse function, just like this f inverse of a represents an element in the range of the inverse function. So just some notation here. Now, if I find the equation of the tangent line at this point, f inverse of a on the original function, then it has a slope of p over q. Of course, that is the derivative of the original function evaluated at the domain value of my original function, which we get the p over q. Because domains become ranges and ranges become domains, notice how the derivative at this point, which is a comma f inverse of a, domains become ranges, ranges become domains, its slope of the tangent is f inverse prime of a, and it becomes p over q. Notice how this is q over p and this becomes p over q. So the relationship leads us to this theorem that says, hey, sometimes it's easier, rather than trying to find the inverse, it is easier to find the derivative of the inverse function as a relationship between the derivative of the inverse function, as a relationship of 1 over the derivative of the original function, evaluated at the value, this domain value that produces this range value. So that's basically the gist of it. So let's look at this example graphically, and we're going to sketch the inverse. Now remember, domains become ranges, ranges become domains. So I take this point, which is -2, 0. When I do the inverse, it becomes 0, 0, and I wrote 2. It becomes 0, -2. So I'm going to go to 0, -2. So that's where that point went to. Another point on this graph is -1, 1. And its inverse is going to be 1, -1. So I'm going to go to 1, -1. Another point on my original graph is this point, which is 2, 2. Well, that doesn't really do much. It's going to be 2, 2. And here is my inverse function. So this is a graph of the inverse function. Now, if I wanted to know what the graph of the inverse function looks like, this is one of the ways that I can do that. If I wanted to estimate the derivative of the inverse at 1, then I would put 1 in, which would be here. This 1 is, let me tell you where it's coming from. That's the input of my inverse, but it is the output for my original function. So that's the relationship. If I wanted to estimate this slope looks like it's probably a 1 to 1. I'm going to guess probably, maybe not, but kind of close to maybe a 1 to 1, not drawn well, maybe a 1, so up 1 over 2 or 1.5 or something like that. And this one of the original function, the slope of the original function, looks like it's this slope of the original function looks like it is up 1 over 2 approximately. That means this one, if I drew it a little bit better, let me draw it just a little bit better. Looks like it's probably going to be almost, this slope is going to be up 2 over 1. So notice how the relationship here is that they become reciprocals. So then what we can do is we can find the derivative of the inverse function by figuring out what the derivative of the original function is. So if my x is -2, I'm doing f of -2. This is going to give me 6 multiplied by -2 minus 1, which gives me a -13. So my ordered pair of my original function is -2, comma, -13. Now my inverse function becomes -13, -2. So if I wanted to find dx of f inverse of, and notice I put -13 in here, this will be equal to 1 over the derivative of the original function evaluated at the input that is associated with that -13. And the input that's associated to the -13 is -2. So I would find the inverse. So I'd just find the derivative of my original function. So f prime of my original function is just 6. That means that this is going to be 1 over 6. And that makes total sense, right? Because this is a line whose slope along the line is going to be 6. And then the slope of the inverse must be the reciprocal, 1/6. So that makes total sense. And I didn't have to find the inverse. Now I could have, but I didn't have to. So let's take a look at the next example here. So again, if I were to put in x is equal to 1, right, f of 1 is going to give me 2 multiplied by 1 raised to the third minus 3, excuse me, which gives me -1. So the ordered pair is 1 as the input, -1 as the output. For the inverse then would be -1, comma 1. So then dx of f inverse of -1, because that is the input for my inverse, which is the output of my original function, is going to be equal to 1 over f prime evaluated at 1. 1 being my input, that produces -1 as the output. So let's go ahead and find the original derivative. So f prime of x is going to give me 6x squared. So 6x squared. So then this is going to be 1 over 6, 1 squared. So my slope is going to be 6. It's also 1/6. Now, if I go to my original function, f prime evaluated at 1 is 6. So this is the slope of the derivative at the point 1, comma, -1. And this is the slope of the inverse at -1, comma, 1. Now, this allows us to extend out the power rule as well. So now we can do the power rule derivatives when I have exponents that are not integers. So now I have powers that are rational exponents. So that means that I can now find dx of x raised to the 1/2, which, as you know, is a square root of x. And this is going to be, extending out the power rule, still the power is going to come down out front. So that's 1/2 x raised to the 1/2. And I'm going to subtract off 1, which is 2 over 2. Now remember, my denominator is 2, so it's going to be 2 over 2. And so my final answer is 1/2 x raised to the -1/2. And I can leave it like that, or I can write it as 1 over 2x raised to the 1/2, which I can leave it like that too. Or I can write it as 1/2 the square root of x. And I'm fine with any of those answers are totally fine with me. Now, since we now can find the derivatives of inverse functions, provided, of course, that they have the inverse, they're 1-to-1, then that means that we can find the derivatives of inverse trig functions. And we know from our pre-calculus 2 class that for these to have inverses, we have to restrict the domain of the original function, which means that the range of my inverse will be restricted from the domain, because domains become ranges, ranges become domains. And these are the derivatives of inverse trig functions. You don't have to memorize these. All the rest of them you have to memorize, but from this point out, I'm going to give these to you on the test, so don't have to memorize those. Now, let's go through some of these examples where I'm asked to find the derivative of the inverse because, and I say because, see when I see this A, that is really when I see this A, because remember how we noted this earlier, f of A gives me the x value. So in other words, my original function would have been x going in and A coming out. So these A values, when you see it in this form, it's not x equals, it's the A values. These are the output values. And so I need to figure out what the input value is to find that as the output. So what I'm going to do is I'm going to say, okay, f of some value A is going to give me 2, which is going to be equal to x squared plus 3x plus 2. So in other words, I have 2 is equal to x squared plus 3x plus 2. So x squared plus 3x is equal to 0 because I've subtracted 2 from both sides. I'm going to factor out an x, and I have x plus 3 is equal to 0. And so my answer is x is equal to 0 and x is equal to -3. So there are 2 places in which x is going to be equal to a value that produces 2 as an output. So by default, we know that a quadratic is not 1-to-1, and this restricts my domain, so it will be 1-to-1. And in fact, they're restricting it at the vertex. That is the vertex. And if I were to find the vertex, I would find that the x part of the vertex is -3/2. All right, so because I'm restricting it, so that is -3/2 or larger, I'm not going to consider that. So my x that produces 2 is 0. So the ordered pair is 0, 2. Now notice, this is the same thing as finding, they want the f inverse of 2, and they want me to find the derivative of it. That is the notation of what they're asking me to do. So in other words, I need to find f prime of x, which is going to give me 2x plus 3. F prime of my input of 0 is 3. That means my answer, this is my answer, f prime of A, which is f prime, or f inverse, excuse me, it is, I'm going to do all my notations here correctly, it is d dx of f inverse of 2, which, let me just erase this, which is going to be equal to, this is going to be equal to 1 over f prime of 0. And so we know that f prime of 0 happens to be 3, so my answer is 1/3. And I was able to find my derivative of the inverse at that output without actually having to find the inverse. Now, I could have found the inverse. It's just going to be some algebra, and it wouldn't be too bad. Now, B is a little harder to find the inverse, so we're not going to find the inverse. Instead, we're going to do exactly what we just did, and we're going to start out with the first thing. The first thing is find the x that produces A. So I have x plus the square root of x is equal to 2. Now, so here's some algebra, and so I'm going to go ahead and I'm going to subtract x from both sides. So I have the square root of x is equal to 2 minus x, and now I'm going to square both sides. Now that I have my square root by itself, I'm going to square both sides. And I'm going to get x is going to be equal to, and I get 4 minus 4x plus x squared. I'm going to bring the x to the other side, and so I have x squared minus 4x minus or plus 3 is equal to, wait a minute. So I was subtracting from the wrong thing. So minus 5x plus 4 is equal to 0. So we know this is going to be x minus 1 and x minus 4 is equal to 0. So my choices are x is equal to 1 and x is equal to 4. So I have to check to see which one of these is going to produce 2. So I'm going to check. I'm going to check these now. I didn't have to check it on my last one because I started out with a quadratic. This one I'm not starting out with a quadratic. I'm starting out with a function, an algebraic function. So if I put 4 plus the square root of 4, this does not equal 2. So I know that 4 is not the input that is going to produce 2 out. Now I'm going to check the other one. So I have 1 plus the square root of 1. This does indeed equal 2. So the one that I'm going to use is 1. So after I've found the x that produces the a, the next thing I'm going to do is find f prime of x. So my derivative of this is going to be equal to, the derivative of x is 1, and then plus 1/2 x raised to the negative 1/2. The third thing I'm going to do is I'm going to find f prime of that x value, which in this case happens to be 1. So I put that in and I have 1 plus 1/2, 1 raised to the negative 1/2, and so I have 3/2. The fourth thing I'm going to do is actually find the derivative of my inverse function. So I'm going to find d dx of f inverse of x. And we know this is going to be 1 over f of the value that produced that x. I know it's kind of like alphabet soup, so I'm going to put a here, put a right here, and this is the x that produced that a. So this answer is going to be the reciprocal of 3 over 2, so it's going to be 2/3 is my answer. So that's my answer for B. Let's go ahead and do the answer for C. And so again, the first thing I'm going to do is find the x. So I have f of x is equal to x plus the sine of x, which is equal to 0. So the only way this is going to work is when x is equal to 0. Because when the sine is equal to 0, the sine of the angle is equal to 0 when x is equal to 0 or pi. But if I used x is equal to pi, pi plus 0 does not equal 0. So my only answer is this. Now my second part is f prime of x. So this is going to be 1 plus the cosine of x. Third thing I'm going to do is f prime of my 0, which is going to be 1 plus the cosine of 0, which is going to be 1 plus 1, which is 2. The next thing I'm going to do is find d dx of f inverse of 0, which this happens to be 0, 0, which is equal to 1 over f prime of 0, which happens to be 1/2. And that is my final answer. Let's take a look at my last example here before we go on to finding the equation of the tangent of the inverse. So the first thing again I'm going to do is find the x that produces the tangent of x. Plus 3 times x squared is equal to 0. Well, tangent of x is equal to 0 when x is equal to 0. So again, my x that produces 0 is going to be the ordered pair of 0, 0 again. So nothing surprising there. Second thing I'm going to do is find f prime of x, and the derivative of tangent is secant squared of x, plus, and then I have 3 times 2, which is 6x, so 6x. Third thing I'm going to do is find f prime of 0, and secant is the reciprocal of cosine, so it's the cosine of 0 is 1, the reciprocal of 1 is 1, so that's 1, and then plus 0, so the answer is 1. Oh, this is going to be lovely. My last and final thing is I'm going to find d dx of f inverse of my 0, which is 1 over f prime of 0, which happens to be 1. So that is that answer. Now what we're going to do is we're going to find the equation of the tangent line at a point on the inverse. Now be aware that this point P is the point on the inverse. So the original point, we're going to call it Q, which would have been on f of x, would have been 8, 2. So be aware that P is on the inverse. Q would have been the original function, and so it would have been 8, 2. So remember that domains become ranges, ranges become domains. Just something to be aware about. Because of the fact that they're giving me both the input and the output for the original function and its inverse, then I can skip the first step and go right to finding f prime of x. F prime of x is going to be 1/2 x minus 4 raised to the negative 1/2. Then I'm going to evaluate f prime at 8, because that is the input of my original function, which is going to be 1/2. And then I have 8 minus 4 raised to the 1/2. So in other words, I have 1/2. And then I have 8 minus 4, which is 4. The square root of 4 is 2. So this equals 1/4. Now I'm going to find the dx of f inverse of 2 is the input of my inverse. So this is going to be 1/f prime of 8, which is 1/4. So my slope of the inverse function at that point, 2, 8, the point being on the inverse function, is 4. Now, we know that y, the equation of the tangent line, is y is equal to m x minus x naught plus y naught. Because we're looking for the equation of the slope of the tangent of the inverse function, we're going to use these points as my x naught and my y naught. So y equals 4, that's the slope of my tangent of the inverse at the point 2, 8, the point being on the inverse, of x minus 2 plus 8. And that is my final answer. Now remember, the point Q is the one that would have been on my original function, which is 2, negative 8. I just need that to remind myself, because I have a tendency to switch them, that when I find f prime of x, I'm going to input 2, not negative 8. So f prime of x is going to be negative 3x squared minus 1. So then f prime of 2 is going to be negative 3 times 2 squared minus 1, which is negative 13. So then the dx of f inverse of negative 8. See, I told you it's easy for me to do that. Negative 8 is going to be 1/f prime of 2, which is 1/negative 13. So then the equation of my line is y is equal to negative 1/13 x minus 8, and then plus 2. And that is my equation of the tangent line. Do one more, and then we're going to find derivatives of our inverse trig functions. It looks like we have a little bit of chain rule thrown in there for fun. So let's go ahead and remember that our q, which is on the original function, is 1, 16. F prime of x is 4. X cubed plus 1 multiplied by 3x squared. Remember the chain rule. So f prime evaluated at 1 is going to give me 4. Oh, don't forget that is cubed there. 1 plus 1 cubed multiplied by 3 times 1 squared, which is just 3. So I have 4 multiplied by 2 cubed, so that's 8. So I have 32. Get my calculator out, because sometimes I can do this on the fly and sometimes I can't. So 32 times 3, which is 96. So dx of f inverse of 16 is going to be 1/f prime of 1. And so it is 1/96. And so my equation is y is equal to 1/96. X minus 16 plus 1, and that is the equation of my tangent line. Now, let's go ahead and start doing the derivatives of the inverses. Now, I give these to you. I just want to remind you where they are. I probably should have put them down here later. So I give these to you. It is the derivative of sine inverse, and I actually prefer if this was a u, so I could remember by using the chain rule I have to multiply by u prime. But, you know, you just have to remember that you have to multiply by u prime. So the derivative of this, so dy and dx of sine inverse, is going to be 1 over the square root of 1 minus x squared squared. And then don't forget the derivative of x squared, and so it's multiplied by 2x. And that is the answer for that one. It's lovely, lovely. Now this one includes the chain rule. That one did too, but this one has a little bit more. So dy dx is equal to 3, 1 plus the tangent inverse of x raised to the 2. Now I'm going to do the derivative of the inner function, which is 1 plus the tangent inverse of x. The derivative of 1 is 0, so I don't have to worry about that. And then it's going to be multiplied by 1 over 1 plus my x, the quantity squared. The derivative of x is 1, and so that is my final answer. Taking a look at y here, so on C, dy dx. Well, actually I'm going to back up just a little bit. This is the same thing as the tangent inverse of x raised to the negative 1. It's not a power to power. We're not going to say it's tangent raised to the positive 1. That is not it. So when we do this one, this dy dx is going to be equal to negative 1. The tangent inverse of x raised to the negative 2. That's the chain rule. Now I'm going to do the derivative of the inverse function, which is the tangent inverse. So that's times multiplied by 1 over 1 plus x squared. That's my final answer. Now I can clean that up and that's fine, or you can leave it just like that. This one is the product rule. Product rule. So I'm going to do the derivative of the first one. So dy and dx is going to be the derivative of the first function. The derivative of cosine inverse is going to be negative 1 over the square root of 1 minus 2x, the quantity squared, multiplied by the derivative of 2x, which is 2. Multiplied by the sine inverse of 2x. That's my first derivative. Plus, now I'm going to do the derivative of my second function, which is the sine inverse. So it's going to be 1 over the square root of 1 minus 2x, the quantity squared, multiplied by 2, multiplied by the cosine inverse of 2x. Now this one you could clean up a little bit. You could factor out a 2. You could factor out the 1 over the square root of 1 minus 2x squared, and that'd be totally fine. Or when you do the derivative test, you can leave it just like this. Okay, so here, it's kind of different, kind of same, kind of different. They're telling you my input is 6 and my output is 2. This is my Q. My P would be 2, 6. What they want me to find is f inverse of 2, the d dx. We know that this is going to be 1 over f prime of 6. And they give this to me. That's this. So this is going to be equal to 1 over 1/3. And so in other words, the answer is 3. So I didn't even have to do any work on this. I just have to figure out what it is that they're giving me and parse it out. All right, same thing. My Q is a square root of 3, 1/2. My P is 1/2 the square root of 3. My derivative of my inverse, d dx of f inverse of the square root, or actually it is 1/2, is equal to 1 over f prime of the square root of 3, which is equal to 1 over 2 over 3, which is just 3 over 2. These are so lovely, not having to find the inverse first. My last one, my Q, is the point 1, 0. My P is the point 0, 1. So they want me to find d dx of f inverse of 0, which is 1 over f prime of 1. And they tell me f prime of 1 is -2, so it's 1 over -2. And that's my answer. And that's it for this section. So it's really not that bad. finding inverses, the derivatives of inverses, if you don't have to find the inverse first. It saves so much time. And that's it.